Okay, if you don't have any question, we can start lab 3. In lab 3, we want to practically reconstruct a cross-sectional body image from its sinogram using Fourier analysis. The input data is the density value for a sample cross-sectional image of a patient skull. The input image, the input image is something like this. It shows a sample cross-sectional image of a patient skull. This function here generate the input image mathematically. So if you have a look at class sinogram, you can find this function here. Yes, here this function generates the density points for each x and y, the density value of each x and y point in this image. In this lab, we first create the radon transform of this image here. Then we will try to reconstruct the skull image from its radon transform. We have one support class named display sinogram FT. In this function, we have in this class we have some function to graphically display sinograms and anything we need to display the sinograms and the outputs. We have everything here. So please download the class from this hyperlink and import it to your IDE. The next class we will use in today's lab is named Sinogram. In this class, we have the main function and some helper functions such as the back projection function, as we discussed in the lecture. Here we have the main function and then back projection implementation, this function to generate the density function fxy, and one norm function. I will explain this norm function later on. In the main function, here we have a for loop. This for loop is responsible to read the cross-sectional image and create this density matrix. So this for loop reads somehow this input function, this input image, and store the densities values in the matrix named density. The next section of code calculates the radon transform using this density matrix here. So this section of code is simulating the actual process of doing a CT scan. So if you remember, in the CT scanning, we take different measurements from different angles of a piece of body. This code here simulates what a CT scanner performs. As we can see here, the first line in the for loop finds the theta angle of the point. And then here we have the R values. At the end, we have a matrix like this representing a sinogram. So this sinogram creates using this density matrix here. And as I mentioned earlier, these two inner for loops somehow simulates what CT scanner performs. As we can see here, the first index in this matrix corresponds to theta values, and the second one represents R values for the input image in this scenario. Since the radon transform P theta R is in polar grid, here we have all computations in polar format. So here we have sine and cosine functions, and we obtain the theta angle and R labels of the detectors. In this section, we have an omitted code. In the second part of the lab, we will insert the sinogram, the filtered version of sinogram here to obtain the higher quality of cross-sectional image. But anyway, you know, in the first attempt, before applying any filter, please run the code to reconstruct the skull image. Here, the skull, to reconstruct the skull image here, using pure or unfiltered radon transform. Here, we create the pure or unfiltered radon transform. So in the first attempt, we don't apply any filtering on this sinogram, and we exactly use this sinogram we use the pure sinogram to reconstruct the image using back projection sum. As I mentioned earlier, this back projection sum has been implemented in this class. So we don't need to implement this back projection. Everything is ready. We only call this function, and we use the pure sinogram of image to create the cross-sectional image and display it. Here in this section of code, we normalize the original densities, because the original densities are somehow normalized. That is why before displaying the cross-sectional image, we have to do the same normalization on the density on the densities. It's just, you know, a pure normalization, because here the range of densities in a particular interval. So we normalize this projection to somehow normalize each point in the uh, obtained density function. So this is a kind of normalization step, and as we can see, we apply to the densities before displaying the back projected sinogram. So here in the last part of code, we can see the reconstructed image of this scar. So in the first step, we have density function. We create the density function. This density function is this image. We display the input image. Then we create the sinogram from this using this density function. This is what CT scanner performs for us. But anyway, we don't have any access to any CT scanner. That's why we have to simulate what a real CT scanner performs. After creating this sinogram, we apply back projection sum on the sinogram and display the reconstructed image. This is what you should do in the first part of the lab. Here you can find, the details I've already explained. In the next attempt, you are supposed to filter the sinogram using fast Fourier analysis, as I explained in slide number 18. If you remember in that slide, I listed 3 steps, how you can filter a sinogram. So in this skeleton, you should implement these 3 steps here. So here, you first apply 1D FFT on each row of the sinogram to obtain P tilde. Then you use this for loop to multiply each element in the P tilde by absolute value of K. And at the end, you will do an inverse 1D FFT on each row of P tilde to obtain the P theta R function. So here you should complete this skeleton code using slide 18. And to apply filter, you can use these 2 for loops. So step two in slide 18 can be implemented using these 2 for loops. In fact, these 2 for loop here multiply each element in the sinogram by the absolute value of K. So complete this skeleton code and then fill this part of the main function using the filtered back projection skeleton here. So this skeleton filter the sinogram we have here. Yes, this sinogram. Filter this sinogram, and after applying back projection sum, you can obtain the filtered density function, and you can compare this image you obtained from the filtered sinogram with the pure image you created using the pure sinogram. Uh, as an exercise, you can apply low pass or high pass filters to the radon transform. If you remember, in lab 1, we did such low pass or high pass filters. Here we defined a cutoff point, and then we set all the points beyond this cutoff point to 0. So as an exercise, you can replace this multiplication step by a low pass filter or high pass filter, and then use the new version of filtered sinogram to create back projected sinogram function or back projected image. So this is exercise. So in the first step, creates the density function or the cross-sectional image without any filtering. Then in the next part, complete this skeleton code to apply a filter by multiplying each element in this sinogram Fourier transform by the abstract value of k value, and generate the cross-sectional image using the filtered sinogram, and see how look like the output. And at the end, you can apply high pass or low pass filters to see how these kind of filters impact the output image.